And we are live on YouTube. Please go ahead, enjoy your session.
Hi, everyone. So welcome to this session of chess. Just a sec. So we will present our first speaker. We are going to have 6 papers today, and our first speaker is Iggy. Please go ahead, Iggy Bankhoff.
All right. Hi, everyone. So I'll be talking about concrete quantum cryptanalysis of binary elliptic curves. I think it's a bit removed from the other topics today. So I'll really be focusing on why what we're doing is important and the results we get, more so than the method, which will take a bit too long to explain. So I want to thank my co-authors, of course, Gustavo Benegas, Dan Bernstein, and Tanja Lange. And so let's get to the subject matter. So as you're hopefully aware, Shor's algorithm on a sufficiently large quantum computer will break RSA and elliptic curve Diffie-Hellman, the two currently widely used asymmetric cryptographic systems. And so in this talk, we really will be looking at how big do you need to make one of these quantum computers to actually break these systems. So if we say have X qubits, then we can say these systems are broken. And so there's been some previous work done in the field. There's very recent work both in RSA and prime field elliptic curve Diffie-Hellman. And we are specifically going to be focusing on elliptic curve Diffie-Hellman. And so our results, we measure 2 ways, similar to how we measure normal circuits. We measure the qubits, space. Qubits stand for quantum bits. And we measure the time, which we measure in gates. And in quantum computing, we really consider one gate much more expensive than the other gates. And that's the Toffoli gate, which is at least 7 times more expensive as the second most expensive gate, but can be considered even more expensive. And so we will be optimizing for these 2 measures. As I said, we made these algorithms. So what we made were point addition algorithms. And these point addition algorithms, they basically are the biggest step in Shor's algorithm over binary elliptic curves. So we treat kind of like Shor does some quantum stuff. They need to do a whole bunch of point addition, specifically 2n+2. And then you need to do a little bit more quantum stuff to really get these results. And we really focused on these point additions. So if we look at our results, you can see the number of qubits here. And when we talk about qubits, here in this paper, we talk about logical qubits. So if you see somewhere that Google or IBM or whoever has created a quantum computer with 2000 qubits, which is reasonable in the next 10 or so years, they are likely going to be talking about physical qubits. And physical qubit, you need a lot of physical qubits to simulate a logical qubit. And also the time, the longer you have to keep your memory basically around, also the more physical qubits you need. So, but we focus on physical qubits. So you can see, for example, if we have for n equals 283, you need about 2000 logical qubits. All right, so these are our results, our normal results. Now, what you can do is do some classical pre-computation. And depending on how much classical pre-computation you want to do, we optimize here for a specific implementation of what we call a quantum random access memory lookup, which is basically looking up classical random access memory in a quantum circuit. And so you can see that, for example, if you have a window size of 14, for again, n equals 283, you can see a speed up of, if you go to the previous slide, roughly times 14. You need a bit more because a bit more qubits than an exact division by 14, because you need some extra Toffoli gates to do this quantum random access memory lookup. And again, we also need to pre-compute a number of points, but this number of pre-computed points is relatively low. All right, so how do we feel about our results? Well, we currently feel that our results look very good for our based on our efficient division and multiplication algorithms, because just like in regular point addition, on quantum computers, also division really is the most expensive steps. And again, I've repeated the results like in for any n here. And so, yeah, I think we have a pretty good idea of how big we need to make a quantum computer in order to solve binary elliptic curve Diffie-Hellman. And thank you for your attention.
Thank you, Iggy, for your interesting talk. So we have some time for questions.
If you have questions, please post it on the Zulip, and Kay has already posted a link there.
Meanwhile, I have a question for you, Iggy. So how would be the comparison of binary elliptic curves with prime elliptic curves in RSA? In your opinion, which one would be broken first?
Binary, I think the order is binary elliptic curves, prime elliptic curves, RSA, because you work over smaller fields in prime, in basically any elliptic curves than you do in RSA. So that's more efficient to do on the quantum computer. It's more efficient to do on your normal computer to do ECTH, but it's also more efficient to break on a quantum computer. That's not a reason not to use ECTH. By the time we have big enough quantum computers to break prime ECTH or even binary ECTH, we likely will be very close to also having a big enough quantum computer to solve RSA. So by the time we have one of those, you really should be using post-quantum crypto.
Right. And one more question, Iggy. What about isomorphisms? Like, for instance, Koblitz curves, are they easier to break because you can take advantage somehow of the isomorphism?
So in this case, they're already polynomial time. So you can, I don't have the answer for you right now. Intuitively, the answer is, of course, yes. But we're dealing with polynomial time calculations here. So the speed up is probably not very large compared to the speed up you would get for an exponential algorithm.
Right. So I was just guessing if Koblitz curves are, for instance, easier than regular binary elliptic curves to break using a quantum computer, or the difference is tiny. This is what you're saying?
We haven't looked at this, so I can't say for sure. I would wager that you would get you would maybe get the speed up, but I don't want to say anything how big the speed up would be. I would guess it's not super significant, so that the time it will be broken. So again, here our results are basically, for example, 2000 qubits for logical qubits for n equals 283. For a similar result with Koblitz curves, I think you will see a similar number of qubits with maybe a significant speed up in the number of Toffoli gates.
Okay, thank you very much, Iggy. Some more questions that we have for Iggy?
I don't see any questions, so maybe we could continue.
Okay, thank you very much once again. Let's thanks the speaker once again. Sorry for the bumpy start. And we are ready to move for the second paper of this session. This session has 6 papers, and the next one is Online Template Attacks Revisited by Alejandro Cabrera Aldaya and Billy Bob Bromley. And the speaker is Alejandro. Alejandro, could you start, please?
Thank you, Francisco. Hi, my name is Alejandro. I'm going to do a short talk about the paper Online Template Attacks Revisited. Regarding elliptic curve cryptography, scalar multiplication operation is one of the main objectives for side-channel attackers. Regarding the main targets are the number of iterations this algorithm executes and the conditional operation on the scalars, like the ones highlighted in the algorithm. Okay, template attack are a technique in the side-channel attack field where the adversary has access to a template implementation very similar to the target device. The adversary this way can control this implementation. This means they can capture template traces for any chosen keys. Okay, template attack can be classified depending where the template traces are created. In the classic variants, template traces are created before the target trace. So while online template attack, the template traces are created on demand. That means after the template trace is captured. Previous works on online template attack focus their research on power consumption and electromagnetic leakage. That means they can exploit address and or value based leakage because those side channels inherently leaks them. However, in the microarchitectural realm, value based leakage are not common at all. Therefore, in these scenarios, attackers should rely on address bus leakage only. That means non-constant time code. As part of this research, we revisit previous online template attack regarding attack input, direction, requirement, countermeasure, and leakage sources. Regarding attack input and direction, in previous works, the authors considers that the adversary knows the starting state, highlighted in green here, then continue the attack in the forward direction. We extend it to the case when the attacker knows the last of processed state, then execute the attack in the backward direction. This idea is very similar to the projected coordinates attack. However, a backward online template attack can perform a full scalar recovery, while the other attack, they cannot. Moreover, it can be even generalized further to the case when the attackers know any intermediate state processed by the algorithm, then execute the attack in any direction. As part of this research, we propose an evaluation framework to assess if a particular implementation is vulnerable to online template attack and to which degree. As part of this evaluation, we propose several metrics that are described in the paper. Okay, after the theoretical side of the research, we analyzed 3 open source libraries regarding online template attack. In particular, we focus on 2 side-channel page tracers and copycat that belong to the class of control side-channel on trusted execution environments. As template implementation, we use an emulator based on trace grind, where that giving an state, the trace grind returns an emulated trace of page tracer and copycat. Okay, we performed extensive analysis on these libraries using different cryptographic schemes, scalar multiplication algorithms, as the table shows, different process selection, and different states. The conclusion is that there is online template attack exploitable leakage everywhere in these libraries. Therefore, if non-mitigations are considered, they can be exploited using these side channels. After the analysis of the libraries, we also execute real attacks on these libraries. For this task, we developed XGS enclaves for each of them, and then use the XGS step framework to capture page traces. On the other hand, as attacker environment, you use the same emulator based on trace grind. This means that during the template matching phase, we were comparing real traces from XGS enclaves with emulated ones, and the results were perfect. As the table showed, we executed 100 attacks per library with full scalar recovery in mind, obtaining a 1% success rate in all cases. We tested several methods regarding how the attack works, state and scalar base, also different directions, and different probability math functions of the analyzed combination. If you are interested, there is a proof of concept of this attack using the scalar approach that can be found in this QR. The main conclusion of our work is online template attacks are very powerful against software implementation. This implies that implementation should be secure over all layers in the stack. Online template attack can work in backup direction, starting from any state. Finally, well, randomizing the point might not be sufficient to prevent them. Thank you.
Thank you, Alejandro, for your interesting presentation. We have time for more questions. Do we have questions for Alejandro? Meanwhile, Alejandro, I have one question for you. Could you give us the intuition why going backwards is more powerful than going forward in the forward direction?
Oh, maybe I didn't explain it correctly. It's not, let me show.
Yes.
Going backward is more powerful than projective coordinate attack, but it's not more powerful than the forward direction. Actually, the backward case is harder than the forward one, because in this step, when we are reverting the operation, we get more candidates from the state to be considered. So we have to capture more template traces. But what I was saying in this slide is that backward online template attack is more powerful than the projective coordinates attack of Nakash et al. From several years ago.
No, thank you for the clarification, Alejandro.
Yeah,
yes, and one more question. What about the countermeasures? What would be the suggested countermeasures? Again, if you can explain a bit more, please.
Yes. Okay, the countermeasures especially are regarding preventing the process operation, that is the operations that process the state, that made the point operation, prevent that they lead this processing state. They can be done, for instance, using the hiding approach, but it's not trivial for power and EM side channels, because those side channels is difficult to remove that kind of leakage. However, in the microarchitecture realm, in the software implementations, constant time code should be sufficient. So it's feasible to do it in this kind of implementations. On the other hand, we have in the masking approach, when we can randomize all states, for instance, using projective coordinate randomization too. So depending on the scenario, the developer can choose any of these approaches.
But masking is expensive, right?
Yes, masking is expensive. We're not trying to convince any library to randomize all states. But
Okay.
at least the first and the last one.
Okay, thank you, Alejandro. Some more questions for Alejandro that we may have?
I don't see any other, no, I don't see any other questions.
Okay, thanks again, Alejandro, for the nice presentation, and then we move to the next paper.
Thank you.
Yes, our third paper is of this session that has 6 in total, is time memory analysis for parallel collisions search algorithms. The authors are Monica Trimoska, Sorina Ionica, and Gil Deken. And the speaker is Monica Trimoska. Please, Monica, could you start?
Hi, thank you, Francisco. So yes, as you said, we're going to talk about some time memory analysis for parallel collision search algorithms. And so first, let's see what is a collision in this algorithm. So given a random map F from a finite set S to that same finite set S, we call a collision any pair of 2 elements, say R, R prime, in S such that F of R equals F of R prime. So ideally for these algorithms, we need F to be a random mapping. And also, as we know that as per the Birthday paradox, we can, the expected number of steps until a collision is found should be about approximately the square root of the size of the field S. So most classically, you have the Pollard-Shaw method, for instance, that is a collision search algorithm. Now, in the on the application side, we have both applications that require one collision and other applications that require multiple collisions to be found. So in the one collision case, we have the elliptic curve discrete log problem. In the multi-collisions case, we have more historically the attack on 3DES, and then also the ECDLP, but in the multi-user setting, or more recently, the computational suprasingular isogeny problem. In our paper, we concentrate more on the ECDLP. Our implementation is done in this way. However, the time memory analysis go both for the one collision and the multi-collision attack. So in the multi-collision attack, think maybe ECDLP in the multi-user setting, what the implementation could do. So now the parallel version of the polar throw method is proposed by Van Oschet and Wiener. And here, instead of having only one walk created with this random function f, we have each thread that creates a random walk starting from a different point on the curve. And while they do this walk, they also store some points so that they can discover a collision when a collision occurs. Now, of course, we couldn't store all of the points because that is too costly for the memory. So what Van Oschet and Wiener proposed is to store only a proportion of the points that are called distinguished points. They just have some distinguishing property that is easily testable. And then we also have a very important parameter in this algorithm, which is the theta, the proportion of the distinguished points that we have in a set S. So this is a choice that will impact both the memory and the time requirements. Now, we also do, in the paper, we do some time complexity analysis. You can check it out there. Mainly, we revisit the proof of Van Oschet and Wiener. And in the multi-collision case, we give formulas for the expected time when you need to find multiple collisions and when the memory is limited. Okay, because in the multi-collision case, the memory kind of becomes the bottleneck. And so, our formulas show that the number of points that we can store is actually not only important for the memory part of the algorithm, but also for the running time. And this is why later we concentrate on improving the data structure where we store these distinguished points. So the requirements that we set for this data structure is that we want it to be space efficient overall. We want it also to be easy to make it thread safe, okay, so that we can divide portions of the structure and lock only a portion of the structure when we insert into it. And also we want fast lookup and insertion. So normally in the literature, you have, as far as we know, you have hash tables. And in this paper, we propose to use an alternative that we call a packed radix tree list. Okay, so it's kind of a hybrid between a radix tree and a chained list. This is just a recall of what a radix tree is. And then we'll go immediately to the implementation part because that is a bit more interesting. So what we do is we construct a radix tree up to a certain level. And then starting from this level, we add the points to linked lists. So each list starts from a leaf on the tree. When you go to the implementation part, instead of constructing the radix tree at the top, we just allocate an array where each slot of the array has the prefix that the radix tree, the prefix of the point points to the index of the array in which you need to store the point. So this structure looks a lot like a hash table. However, the difference is that instead of hashing the key, we use just the prefix of the point, which allows us to save space on common prefixes because we do not need to repeat the prefix inside the point. We already know what the prefix is because we know which slot we are at. Okay, so this saves some space. And then also the stored data, we decided to pack it in a single vector so that we save some more space. And then we have a way to estimate the optimal branching level, meaning what is the exact middle such that we have every slot of the array that is filled, but at the same time, we don't have very long chained lists. And we achieve this using the coupon collectors problem. Now, on the experimental side, we have several experiments in the paper. Most notably, we checked how this works. We compared the PRTL structure with the hash table when we do a multi-collision search with a memory constraint. So say with a memory constraint of 1 GB, we ask both structures to find 4 million collisions. And in all parameter cases, we have the PRTL that had better running times, and this is only because the PRTL is able to store more distinguished points than the hash table. And so if this is interesting to you, you can see more results in the paper, and you can check out the artifact that allows us to create new structures, compare them with the PRTL with the hash table, both on the memory side and on the running time. Thank you.
Thank you, Monica, for your nice presentation. So we have time for some questions.
We do have a question for Monica. Do you know how long the linked lists are roughly in your attacks?
Well, the linked lists really depend on how we choose the level, but if we choose it like this, I mean, I couldn't give you a number because, of course, it depends on the number of points that you have, but we did check how are they distributed, and they're pretty equally distributed. So you can maybe divide the number of points that you will store overall by the number of slots that you have, and it is pretty accurate on how the distribution is pretty well. And it's not negligible. It's not like 3-4 points. It is really the case where you need to have some chained lists.
Okay, thank you for the answer. Some more questions for Monica?
I don't see other questions yet. Maybe
okay.
there will.
Okay, if not, then thank you again, Monica, for your nice presentation, and then we move for the next paper.
Okay, so for the next talk, Sung-Hyun will present about novel key recovery attacks on secure ECDSA implementation by exploiting collisions between unknown entries. Sung-Hyun, please.
Can you hear me?
Yes, we can hear you.
Thank you for introducing. I'm Sung-Hyun, PhD student at Korea University. I will present our work on novel key recovery attack on ECDSA. When ECDSA is operated in real environments, side-channel leakage can be occurred depending on secret. So side-channel attacker can recover secret using the leakage. According to the required number of traces, side-channel attacks are separated into single trace attack or multiple trace attack. Our attack is a new multiple trace attack using leakage from scalar multiplication. Regular table-based scalar multiplication is our target operation. For introducing notation, I will explain how table-based scalar multiplication is worked. A pre-computed table T is used in the main operation. KS is an example of index sequence for table referencing. It is determined for each scalar multiplication according to inputted scalar K. According to the index sequence KS, corresponding entry is accumulated as follows. Then, expanding this final expression, we get a linear expression of each table referencing. Then WS are doubling related terms, and T's are table referencing term. Our attack requires two assumptions. The first assumption is that the number of doubling operation is dependent only on loop index. And the second assumption is that attacker can get sufficient trace on multiple ECDSA signature generation. This is a common sense in view of a multiple trace attack scenario. As we can see later, we only need at most trace one more than the total number of entries in the table. I will give the sketch of our attack in this slide. When ECDS signature generation are performed, attacker can collect trace on scalar multiplication. Then there are leakage on table entry referencing. Through visual inspection or some side-channel technique, the attacker can extract subtrace on it. Then through side-channel technique, the attacker can distinguish the two vertical subtrace, refer whether the same entries or not. This can be possible although there is no information on the table entries. For all vertical subtrace on each loop through pairwise collision attack or other clustering algorithm, the attacker can group and label it. Let's name the label sequence as collision information. On one hand, ECDSA signature expression can be converted into an equation of nonce K. The nonce is an unknown secret, but a nonce equation is mapped to a collision information. This collision information is about relation between nonce. It represents whether two nonce have the same entry for a component or not. Thus, if the attacker can find the linear dependency of collision information, then immediately attacker knows a linear dependency of nonce resulting in 0. And this means that the attacker can recover secret key D. Next slide, I will how attacker can find the linear dependency. For the convenience of explaining, we consider 3x3 pre-computation table as an example. Aforementioned, each trace includes leakage on table entry referencing. Attacker can close a subtrace vertically and get collision information. With this setting, I will how to find the linear dependency in next slide. Attacker has no information on the relation between different group labels. For that, convert the vertical group label in one-hot representation. Since the pre-computation table has 3 rows, a label is converted into 3-dimension vector. Then in this case, collision information is transformed 9-dimension vector. The value of converted vector means that how many corresponding entry in the table is used for constructing the nonce. With only one more vectors than the dimension of the vector space, the attacker can find the linear dependency of the vector by Gaussian elimination. Since linear dependency of converted vector is equal to linear dependency of nonce, attacker can know a linear dependency of nonce resulting in 0, then attacker can recover secret key by simple algebra. In our attack, for finding linear dependency, collision information must have no error. However, clustering error can be possible due to signal-to-noise ratio. Our paper provided that the probability of error is significantly low in ideal environment. Our papers provide a case study on fixed base cum and TSM scalar multiplication for showing our attack can be applied easily. And also provide an experiment as a proof of work in detail. Please read our paper for more detail. If you have any question, feel free to send me an email. Thank you for listening.
Thank you very much for the presentation. Are there any questions for Seung-Hoon?
We don't have yet some questions for the speaker.
In the meanwhile, then maybe I can ask one. So in the paper, you show that you can do an attack with m equals to 2 and say that for larger m, there might be some problems due to noises. So I just wonder whether you can give a prediction on what would be a reasonable m to try.
I'm sorry, what?
Yes, so in the paper, you show that you can do the attack with m equals to 2. And for larger m, there might be some problems with noise. So I just wonder if you can predict what would be a reasonable m to try.
In these days, we are writing next paper related to this paper, and we success clustering on comparatively large class. So I don't know yet. They could maybe need more time.
Okay, no problem. So maybe it could be your future work of future research.
We have one question for the speaker. The question is the following. do you think that the technique would be applicable to microarchitectural attacks?
I don't know enough microarchitectural attacks, so, and I don't detail property of the leakage for microarchitectural attack. So yeah, I don't know.
Okay, thank you.
Are there any other questions?
No.
If
don't have.
not, I think we can move to the next talk. And if there are still questions, feel free to post it on Zulip. Okay, so let's move to the next talk. Efficiency through diversity in ensemble models applied to side-channel attacks, a case study on public key algorithm. Gabriel, the floor is yours. Gabriel? We can see the screen, but we do not hear your voice.
Can you hear me now?
Yes, that's better.
Sorry, thank you very much. So thank you very much for this introduction. So I'm Gabriel. I'm a PhD student from the Ubertian Laboratory in the Thales ITSF. And the work I will present you today is a joint work with Lilian Bossu and Amaury Awar from the Ubertian Laboratory and Alexandre Venelli from NXP Semiconductors. So here, the goal of our work consists in combining multiple deep neural networks in order to enhance a full attack scenario against PKC implementations. But first, how does an adversary enhance a full attack scenario? So to understand this point, let's start by introducing the dataset we consider in this talk. So here we consider RSA implementation that has been introduced by Carbon and al. At CES 2019, such that three countermeasures, namely input randomization, modulus randomization, and exponent randomization, are implemented. And following the work provided by Carbon and al., we know that if an adversary can retrieve a sequence of sec3 values such that sec3 denotes an address index, therefore the adversary is able to emit an hypothesis on the private key bits. So let's assume that the adversary is able to guess the following private key, such that the true one is the following one. If we look carefully at both at the prediction and the true private key, we can observe that some wrong prediction has been made by the adversary. So in order to perform a full attack scenario, she has to conduct additional operation, also named as reminding operations, such that the number of reminding operations depends on the attack scenario the adversary considered. So here in this talk, we consider the alternate attack scenario that we not detail in this talk. But what you have to mention is that this number characterizes the number of reminding operations, such that depending on the epsilon bit value, such that epsilon bit defines the error rate provided on the bits, we can observe that an even slightly improvement on the epsilon bit value can non-negligibly improve a full attack scenario. So here our goal was to find a solution in order to improve as much as possible the epsilon bit value. And a typical approach that is considered in deep learning is called the ensembling approach, so that this approach consists as follows. So here we assume that an adversary is able to design multiple neural networks, here F0, F1, and F2, so that in the ensembling approach, the goal is to combine the probability distribution provided by each of those neural networks, so that if we want to represent an ensemble model as follows, we want to create some interactions between all of those neural networks in order to reduce their correlated errors, because following the work provided by Tamer and Ghosh in 1990s, we know that promoting interactions between the neural network is actually beneficial to reduce the global error, so that the global error refer to the error induced in an ensemble model. So here, our goal consists in finding a new solution, a new loss function, in order to promote interaction between the neural networks during the learning process in order to reduce as much as possible their error correlation, and finally to improve the epsilon bit that I previously introduced. So the ensembling loss we design is called ensembling loss, and it aims at approximating the mutual information between an ensemble model F and a targeted variable Z, such that this mutual information has been introduced by Brown in 2009 and then extended by Zhu and Li in 2010. So here, the goal of our loss function that we can observe here aims at train a neural network such that the neural network converges towards the mutual information and aims at promoting interaction between the neural network during the training process in order to reduce the correlated errors. So then, if we want to evaluate the benefits of the ensemble methods and the ensembling loss on a real case study, we can first assess its benefit by comparing the results we obtain with the state of the art. So in the state, if the adversary considers the state-of-the-art result, first he generates a neural network so that the output of the neural network predict the private key bits, so that in that case, if the adversary considers the state-of-the-art result, therefore he can retrieve 90% of the private key bits. And finally, in order to complete its attack, the adversary has to compute additional operation, and here in that case he has to compute 2 to the power 102 additional operation. In opposition, if the adversary considers the ensembling approach as well as the ensembling loss, here we observe that we have 5 neural networks, so that we promote interaction between all of those neural networks during the training process. And what we observe here is that we first improve the ability of the model to retrieve the private key bits, and also we reduce drastically the number of remaining operations, because here we need 2 to the power 96 remaining operations. But one interesting point is that if we follow the European SOGAIS security guidance, we know that the maximum brute force complexity of around 2 to the power 100 is considered as practicable. So if the evaluator considers the state-of-the-art result, therefore it cannot perform a full attack scenario, and then we can consider the PKC, the RSA implementation as secure. While if the adversary considers the ensemble methods as well as the ensembling approach, therefore the number of remaining operations can be considered as practicable following the European SOGAIS security guidance. So if we want to conclude about this work, first, the ensemble methods are useful because they are helpful to defeat PKC implementation, because as I mentioned, a slight gain in accuracy provides a realistic improvement for a full attack scenario. And in addition, using the ensembling loss is beneficial to the adversary in order to promote interactions between the neural networks during the training process in order to reduce as much as possible their correlated errors, and therefore reduce as much as possible the global error introduced by Tomer and Ghosh in 1996. So thank you very much for listening. If you have any questions, do not hesitate to ask or to contact me over email. Thank you very much.
Thank you for your presentation. Are there any quick questions for Gabriel?
Yes, we have one question. Gabriel, if you are attacking RSA, why not use Henninger-Shaham to correct the errors?
Sorry?
If you are attacking RSA,
yes,
why not use Henninger-Shaham to correct the errors?
We also could use this technique to correct the errors. The mainly point with the ensembling approach is to reduce as much as possible the remaining operation an adversary needs in order to correct the errors. So for example, if we want to use this technique, we can use it, but considering the ensembling loss, reduce the number of corrections we have to make during the attack process.
Okay, thank you.
Thank you very much.
Thank you. I would suggest that we continue to the next talk. And if you do have questions, please put it on Zoom. So Thank you. For the final talk for this session is Russell return address stack-based side channel leakage. And the speaker is Anivans. So please, the floor is yours.
Yeah, thank you. Am I audible?
Yes, we can hear you.
Okay, yeah, I'll share my screen. Okay, can you see my screen?
Yes, we can see your screen.
Okay, yeah. Okay, hello everyone. I am Anirban, and today I'll be talking about our paper, Russell Return Address Stack-Based Side-Channel Leakage, on behalf of my co-authors, Sharni Bhattacharya, Manar Alam, Shikhar Patramish, and Devdeep Mukhopadhyay. So in a nutshell, we combine two artifacts of the computer system to demonstrate a new side-channel attack, and we name it Russell. More specifically, we use the deadline scheduler from the operating system and the return address time from the processor, and use it in collaboration to create our attack Russell, where we eventually attack the ECDSA signature generation algorithm to leak the private signing key. So, schedulers, as we know, it handles removal of processes from the CPU, and there are common types of being CFQ, NOOP, and deadline. But in this work, we particularly focus on deadline scheduler, which automatically preempts a process from the CPU after its required expiration time. So it has found quite wide applicability in real-time operating system, where the user needs this capsys nice permission to change the adjust the scheduling parameters. However, the security implication of this scheduler has never been studied in literature before. So another component that we use in our work is the return address stack. So it is a hardware stack that is mainly used to store return addresses for function calls. So whenever a processor does some function calls, the return addresses are eventually stored on the stack. This stack is actually implemented as a circular LIFO stack, and as is the case with any hardware stack with limited capacity, it can suffer from overflow and underflow conditions. So the first contribution for this work, we propose a generic reverse engineering algorithm where we reverse engineer the size of the stack for any undocumented processors. From this figure, we see that there is a significant jump between the consecutive function calls at function depth 16 and 17. So it shows that the platform we tested our this code on has a RAS of size 16. So next we establish a covert channel using RAS, using a receiver and a sender on the same logical core, where the receiver makes n nested function call, where this value n depends on the size of the RAS, then yields the CPU inside the deepest function without executing a return statement. Then the control goes to the sender, which is processing a bit of zeros and ones, and on processing a 1, it makes a function call, and on processing a 0, it does not do anything. And then again, it yields the CPU such that the control again goes back to the receiver, which now starts executing the unfinished return commands, and then measure the timing latencies for the functions. So in short, what the receiver is trying to do is that it tries to set up the RAS to a known state, and when it gets the power back, it just tries to see whether the state of the RAS has suffered any changes from the sender, and based on that, it tries to understand what are the bits that are being trying to be transmitted by the sender. So as we see in the figure, we have an empirically defined threshold, and whatever the values above the threshold indicate a 1, and the values below the threshold indicates a 0. So we extend this this covert channel to perform a template attack on ECC scalar multiplication, where the victim and the attacker are sharing the same logical core, and thereby also sharing the same RAS. So the attacker again fills up the RAS and gives up control to the victim, where the victim executes the ECC scalar multiplication using Montgomery ladder operation and yields the CPU after each iteration. Then again, the control comes back to the adversary, which tries to measure the timing latency and thus perform the attack. So as we know, the template attack works in two phases. First is the template building phase. So we in this work we target P384 Carver OFSL 1.1.G, which is implemented using Montgomery ladder with conditional swaps and non-adjacent forms. So we make templates using the total number of function calls of bn sub and bn add functions, and then we in the template matching phase we do a chosen plain text attack using the inputs associated with each of these classes, and measure the timing attack, the timing values using our RASL. So here is the snap of a result. This shows the template for 350th bit, where the actual value is 0, and the correct estimate shows that the correct estimate, which is 0, shows that the distributions are almost similar with the template, whereas the wrong estimate, which is 1, that shows that the templates do not match. Now we remove this imposition that the victim needs to yield the processor by using this deadline scheduler. So we get the synchronization to work with the deadline scheduler. So again, the victim and the spy can be executed with a single runtime parameter. And in this case, no synchronization mechanism is required inside the victim code. So basically, the victim and the spy are actually running asynchronous on the same logical code. So in this work, we work in 2 phases. In the first phase, we perform a targeted key recovery of a fraction of the MSB of the nonces sampled by the ECDS signing algorithm. And then we use this partial nonce information with well-known lattice-based cryptanalytic techniques to retrieve the full key. So we target the L MSB bits, and using varying these bits, we get 2 to the power L bit sequences. And then we vary these L bits and perform the ECC operation, whereas the spy process measures the time for each of these operations. And in the template matching phase, we use 500 non-signature pairs to extract 6 MSBs and perform a least square error-based technique to determine the top 5 templates to represent the possible combinations. And using this 500 cross 5 partial nonce information, we create the HNP instances and ultimately solve the CVP instance to get the actual signing key. So as we see in this result, we use 500 nonce signatures, where using RASL, we were able to retrieve somewhere around 200 to 250 nonces correctly, which were enough for our final key recovery. The online phase took around 5 to 7 seconds, whereas the offline phase took around somewhere around 1 hour. So, to conclude, we demonstrate how 2 artifacts can be combined to create a new attack. In particular, we exploit the return address track in conjunction with the deadline scheduler to achieve synchronization between 2 co-located processes. We show as a case study an end-to-end attacks on P384 and P256 curves of ONSL library as case studies. But we want to emphasize that this is not limited to the this particular algorithms or the particular library. Any cryptographic implementation that have secret or data-dependent functions are vulnerable to this kind of attacks. So for more information, we invite you to check our full presentation, which is available on the ISR website, ISR YouTube channel. We also have a demonstration of the of our attack on YouTube. You can check our paper in this link, and if you have any further questions, you can always contact us in this email ID. So thank you for your attention. So if you have any questions, I'll be happy to take that.
Thank you for the presentation. Are there any quick questions for the speaker?
No, no time for questions, and there are no more questions.
If not, then I would like to conclude this session. Let's thank all the speakers and all the questions. And next we have a reception.
Yes, we're going to close out this technical session now. We will then have a reception in the portal application. There are some social rooms for some conversation there, which I hope you'll take advantage of. After all, going to a conference, part of it is to meet new people and talk about other things than just the talks. I will mention that there's a workshop coming up. There's an affiliated workshop, TASER, which is listed on the conference website, and I'll put a link in the chat right here. And I will be putting the link for joining the workshop coming up. Benedict, did you want to say anything about the workshop?
No, thanks. I think Yunteng made a good job this morning. It's at 5 European Standard Time. And
5 p.m. 5
yes.
p.m. Right, I think that's 8 a.m. my time.